Good afternoon, all. I want to welcome you to this presentation I'm going to give on behalf of my colleague, Tayyab Ben Mariam. Dr. Ben Mariam is not available. He has asked me to give this presentation on his behalf. He's our leader on a proof of concept we have launched in ETSI on the subject of autonomics, GANA Autonomics in 5G networks. So once again, my name is Ranganai Chaparaz. I'm based in Germany. I'm a consultant working for Capgemini Engineering. And primarily as a consultant, I'm supporting operators, particularly I'm senior consultant for Vodafone, working together with Vodafone on driving network automation, the autonomics, the GANA multi-layer autonomics framework in ETSI, as well as the adoption in the other SDOs, as we have seen the progress on that. So basically, that's what I would like to talk about today on behalf of Dr. Ben Mariam from Orange, our leader in this 5G PoC program. So as said earlier, the aspect we are addressing within the GANA is about the autonomic management and control paradigm, which we call AMC, that has been adopted in multiple SDOs now. And my colleagues here in this presentation includes Dr. Ekotop from Vodafone, Dr. Ben Radia from Orange, and Dr. Said Sohi from Verizon USA. So what is about the 5G PoC program we are running in the INT AFI working group? It is about the move towards making autonomous networks operation ready based on the ETSI GANA framework to help the industry, especially CSPs, in their journey towards autonomous networks. So it's about operationalizing based on the GANA framework, operationalizing autonomics and the autonomous networks as we see moving forward, as well as mechanizing, monetizing the opportunities we see for the autonomics in 5G based on the GANA framework. Thanks to the fact that both CSPs have benefits, can monetize from the intelligence that the autonomics bring in 5G networks, but also vendors can supply the autonomics software components, including ISVs, can supply the GANA components for autonomics in 5G. First, let me give you an overview on the AFI approach from where we started introducing the autonomics standardization coming from research over the years, supported by the European Commission in FP7 and FP6 programs, but also in the US, the NSF funded projects, as well as other research programs in Asia, working together on autonomics over the years since 2009. So primarily, we moved to ETSI to start work on standardization in 2009. And the approach we took was to have 3 work items, primarily the first one focusing on scenarios and use cases and requirements for autonomics, self-managing future internet, and that then should be the input to drive the work on work item 2 that was focusing on the architectural reference model for autonomic networking, cognition and self-management as a generic reference model. And once we have that reference model, which we are calling the GANA, then the next step is to instantiate the reference model onto target reference architectures that are standardized by different SDOs. So, for example, the BBF, Broadband Forum, ITU, Future Networks, NGN, as well as also architectures in 3GPP. That process of instantiation creates what we call autonomicity-enabled reference architectures. What we see today is that there are frameworks emerging also on the market in the industry, but somehow the issue with such frameworks is that they do not separate implementation details from the generic concepts. So the framework reference model is supposed to be generic, supposed not to be tied to implementation approaches in terms of autonomics. That has been proven in research. And this is the reason why we took this approach of separating the reference model from the work of instantiation in terms of the current and future networks. So that is the approach we took. And then based on that reference model, we have been looking into the reference model impact on emerging paradigms like SDN, NFV, and of course, also taking a look at testing autonomic networks frameworks, trust and confidence in building, trust and confidence building in autonomic networks. That's very important for CSPs, but like I said, this is the approach that we took in terms of separations of the reference model from implementation details. So once we do the implementation, so we are looking at the instantiation process, then we are looking at requirements analysis and specification of implementation-oriented solutions for autonomicity and self-management based on the reference model. That enables the reference model to evolve independently of the network architectures, because today's network architectures may change in the future, especially future networks will bring different types of architectures, but the reference model remains independent or not constrained by network architectures. That separation is what identifies the GANA as a unique framework, because it's a generic model and can be applied to any type of networks to instantiate and build autonomic solutions based on instantiations of the model. I'll show some cases of instantiations. Then we started then the 5G proof of concept based on the GANA itself. So talking about autonomic 5G networks, that's the target. We have discussed earlier in one of the presentations talking about the GANA as a holistic unifying model for autonomic management and control. This is specified in the TS, the technical specification, the standard. We talked about the fact that best practices from different models were fused together to create the GANA model, also from research in Europe, projects of FP7, as well as also in the US NSF funded projects like the 4D architecture, knowledge plane from MIT, and of course the IBM MAPE model. The differences were that if you look at these different frameworks, some focus on low-level control loops, some focus on outer loops that are outside of the network elements. So how to bring a holistic framework that enables developers and innovators to innovate at specific abstraction levels. So for introducing control loops is what GANA has addressed. We have presented about the GANA earlier. We talked about the fact that there are slow control loops that are driven by DEs, decision elements. Those are the autonomic functions, which are very atomic and are modularized, and for different types of addressing management and control. And they drive these slow control loops. We have talked about the fast control loops, that these are driven by DEs within the network elements, the network functions. We said it's the three levels, with what we call GANA level 2, 3, and 4 are the most important, because they can easily be implemented over existing architectures, because these are overlay software modules that can be embedded within the network elements, as well as an overlay of the knowledge plane sitting on top of the network elements of a particular scope or network segment, like the RAN, transport, or core network. And we talked about the functional blocks of the GANA architecture that's also standardized within the TS. Now coming to the example instantiation of the GANA framework on a particular network architecture and its associated management and control architecture, we took a look at the work we did on GANA instantiation on 3GPP, EPC core, and backhaul network. So here we're looking at the hybrid SON, answering the question of autonomics in the RAN, and that means the CSON itself is actually mapping to an implementation for a GANA knowledge plane. We'll talk about that in one of the proof of concepts we did with Serwise on that. Then DSON, these are low-level DEs within the network elements, which are correspondingly policy controlled by the CSON. As following the GANA principles. Then, of course, knowledge planes for the other network segments, transport and core network. So the slow control loops, as we are talking about, and then the fast control loops within the infrastructure, we have talked about that area. So looking at the holistic hybrid model of GANA, what we are saying is that it enables to implement autonomics at various, for various networks at various abstraction levels, and of course, network segments. It guides and offers flexibility to implement us on the choice to implement certain autonomics as distributed software and algorithms within network elements, what we call micro autonomics, and while at the same time being able to choose to implement some algorithms as centralized algorithms in what we call the GANA knowledge plane, the macro autonomics. hybrid zone model is compatible with the GANA as discussed earlier in one of the presentations. We were talking about then the hybrid zone, C zone as a centralized zone, and D zone, which is distributed zone, are considered as an implementation of the GANA model for the run. This we have demonstrated in proof of concepts, and we said also that the framework, the GANA framework, offers definitions of the autonomic functions, the DEs at different levels, and also the mapping to the managed entities that need to be autonomically managed in terms of tuning, in terms of monitoring their behaviors, and then reconfiguring them to fulfill certain objectives. Examples to talk about is like, for example, mobility management DE is associated with the autonomic management and control of mobility management protocols and mechanisms as managed entities. All this is provided within the framework. So that table that we just presented together with the instantiation of GANA onto specific network architectures is what implementers need to then innovate the DE algorithms and implement the DEs. The algorithms we don't standardize, but the DEs we have defined, those are the ones that are standardized. So the types of DEs, the mapping to managed entities. Knowledge plane, we have talked about the knowledge plane as a concept that is is supposed to be then the brain of the network, able to consume events from different type of systems like the OSS, service orchestrators, SDN controllers, Manostech, as well as EMSs, and also to consume events computed or services provided by analytics functions like those that are being defined 3GPP. And then these components need to expose node-bound interfaces to the knowledge plane. The knowledge plane can then program selectively using this type of systems to program the infrastructure. Some of the behavior of the knowledge plane could target to change something in the network using the SDN controller. Some of the more complex decisions by the knowledge plane could be to reorchestrate or to create some orchestration of new services via the end-to-end domain orchestrators. We talked about also integration with other systems like ticketing systems, big data analytics applications that need to be orchestrated by the knowledge plane. We talked about the federations for end-to-end autonomics. Here we are illustrating with horizontal federation of GANA knowledge planes. We've talked about that in one of our presentations where we talked about the need for federation of knowledge planes following the concept of disaggregation. So these knowledge planes can be supplied by different suppliers, including ISVs, including incumbent suppliers or networks. That's what we see. And what's important is to talk about then the federation, which is that the knowledge planes exchange state, coordinate their operations in order to deliver end-to-end self-X properties like self-protection and self-defense and self-optimization end-to-end from the run to the core as driven by the knowledge planes. We talked about also the need for federation, so APIs and protocols for federation between different autonomic management and control domains. That's very important. And then comes the perspectives of the fact that fast control loops help operators in terms of looking at the intelligence that could be embedded within the network functions, because that can reduce that delegation of intelligence by the knowledge plane to the network functions to some degree can help reduce the kind of data that can be sent from the network elements into data lakes, into the knowledge planes, as well as also to reduce and avoid monitoring data dissemination impacting the production traffic, because certain decisions can then be taken by the network functions themselves and not having to force the elements to send a lot of data into the network, monitoring data to the knowledge planes or to data lakes. So that is really very beneficial when you look at the autonomics, the GANA autonomics, what it brings in terms of multi-layer autonomics. And of course, the other thing that is very important, what we're seeing in the operators is really the deployment. We're looking at deployment of autonomics for RAN through advanced SON for 5G, autonomics for telco transport networks and core networks. We're seeing this happening for data center fabrics. We are deploying autonomics, but the benefit we want to benefit really from the full-fledged autonomics is when the solutions are fully conformant, following the GANA principles as such. Some are already following these principles, but we see that as we move forward, we will have full-blown conformance to the GANA principles in terms of the autonomics. We are moving into the era of knowledge plane-driven networking, thanks to these principles of GANA autonomics. The other thing that is important is about disaggregation. We see, for example, in NGMN, it advocates for disaggregated knowledge planes. It's based on the GANA framework that has been adopted in the white paper of NGMN for 5G end-to-end architecture, looking at disaggregated knowledge planes as well. That avoids vendor lock-ins from the perspective of operators, and that's very important because it also opens opportunities for innovation and for DEs and algorithms that come from the marketplace supplied by different types of suppliers. In terms of interworking with different SDOs, the AFI on the GANA framework is interworking with all the different SDOs that they've adopted and are using GANA in the different instantiations of the autonomics in their architectures, as you can see on that. Then coming to the subject of the European Commission's case study of the GANA, which was to move from research to standardization. This is where we came from 2009, and then we built this hybrid multi-layer autonomics and multi-layer AI framework within the same model. So moving towards also certification, testing for ANs, autonomic networks. This is what we are doing. Different SDOs working together with us, including IEEE and GMN, TM Forum, 3GPP, and BPF, particularly also for BPF, the adoption into the AIM framework for autonomic management and control. Our proof of concept is based on this framework, where we look at multi-layer autonomics, autonomics in the infrastructure, thanks to GANA DEs, low-level DEs, and also autonomics in the higher level, which is by the knowledge planes like CSON as a GANA knowledge plane for RAN, and knowledge planes for the PoC and core network, transport networks as such, and then the federation. So, and then look at slice consumers, and then look at how the autonomics perform service assurance as well as security assurance, as demonstrated in our proof of concepts, various proof of concepts, as well as cognitive management and orchestration of network slices for different type of slices. We have done a lot of work on that. Our consortium, different vendors and operators, you can download also the results of our proof of concepts on this website that is given the URL. We started in 2016 with the proof of concept on autonomic service assurance for IoT called Smart Assurance with QualiCloud. Then did the demo 2 in 2018 with Sailwise on CSON as GANA knowledge plane for the RAN, with Big Switch, programmable monitoring fabrics, autonomic monitoring, checkpoint, autonomic security management and control. And then we are moving to the third one, which is really a demo on testing AI and AI in test systems. We did the mapping in one of our work with Cellwise to look at the 3GPP management architecture mapping to the GANA framework, as you can see here, and the results and the discussions on this mapping are found in this white paper that can be downloaded from this site. And one of the things that are very important was also then the mapping of SON functions as specializations of the concept of GANA DEs. So we see here like auto configuration, the specialization of such a DE via these SON functions, as well as different types of SON functions that specialize the GANA DE. This is something that you can find in the white paper as well. And then we looked at connectivity ecosystem for connected cars with Cellwise, looking at SON as a GANA for the RAN, and really in practice in terms of slicing, in terms of network slicing for 5G is what we considered in this proof of concept. So as you can see here, especially the ONIX, the MBTS for the GANA, and then CSON DEs as GANA KP for the RAN. We did a demo on this, and including network slicing, service assurance, and also security assurance using the CSON. The GANA MBTS implementation by Cellwise Provisioning Gateway, we also did a demo on that. Then we also looked at how to use ONAP to implement the GANA knowledge planes and what could be done in terms of enhancing ONAP towards implementation of the ETSI GANA knowledge planes. There is a white paper number 2 that discusses these things in terms of how to use ONAP to implement the GANA knowledge plane and its functional blocks and what needs to be extended in ONAP in order to implement knowledge planes. And it's a good starting point. ONAP can be used to implement ETSI GANA knowledge planes, but we have come up with some ideas on where extensions may be needed. And this is all documented in the white paper number 2 that looks at that, and including also catalogs and how to use them as part of ONIX implementations. The DCAE platform all these mappings on how the DCAE analytics applications and platform, how they can collectively be used to implement the knowledge plane, the ETSI knowledge plane concept. So this is what we have seen, and we have been able to come up with some points regarding the requirements in terms of the use of ONAP, and that can also be combined with ACUMOS to implement the knowledge plane DEs and the platform itself. Then with Big Switch, we were looking at programmable fabrics. That is very important to look at traffic monitoring, pushing traffic to out-of-band fabrics, and then the SDN controllers for the out-of-band fabrics, and then the knowledge plane programming the traffic flow, traffic that is sourced from the production network coming to the centralized tools farm for performance monitoring, as well as generation of KPIs that are then consumed by the knowledge plane, and that forms a feedback into sourcing certain type of traffic, zooming into what traffic is needed to be monitored at a specific time, because the monitoring then becomes elastic and intelligent. And this we demonstrated with Big Switch. Also to integrate knowledge planes with the production SDN controllers and also the out-of-band SDN controllers that control the out-of-band monitoring fabrics. We have done that demo. You'll find that in white paper number 3. This is white paper number 3, and that is not the white paper number 2. And then we also looked specifically at the subject of the capabilities that Big Switch is now Arista, how they can be used to implement what we call then the autonomic monitoring, intelligent monitoring in terms of orchestration of different types of monitoring functions. To push data from the production network to out-of-band via tape and span type of mechanisms, including dynamic spanning via the SDN controllers, and then the probes, how they feed then the KPIs that are computed into the knowledge plane. This is also what we've done. A lot of publications, the white papers are accessible from this website that you see here. We have published about 6 white papers with the results, as well as slides that contain the results of various proof of concepts. Contact details, our colleague Tayeb, Dr. Benimariam is our leader for the proof of concept program for 5G in ETSI, and Muslim Elkotob, Dr. Elkotob is also our contact for this proof of concept program. With this, we'd like to thank you so much. Thank you.